Yeah. All right. Could we settle down, please? Thank you. So the last method that we're going to talk about for nonlinear programming is something called a barrier method. So to sort of give you the distinction between these two methods, so we had in the morning we talked about the penalty method. So the penalty method, what it does, it takes a constraint problem. Could we settle down, please? If you have discussions to do, that outside the class would be much better. Thanks. So we take a constraint problem. Oh, before I begin, there was something on the board here which has disappeared. It was supposed to be, there's some resume workshop that's to be held tomorrow. Jenny has told me that I should reiterate that everybody should be present. And she was going to take attendance, and if you don't show up, you get a third of a grade lower on both of your two courses. So try to be there. It's generally helpful to have better grades than to have lower grades. All right, so what the penalty method did was that it took a constraint problem and converted it into an unconstrained problem. And basically, once it converted into an unconstrained problem, the basic story is that the solution of the unconstrained problem, which let's call it x star of mu, this is the solution that you get when you put a penalty multiplier of mu, is generally infeasible. And it tends towards feasibility as mu goes to infinity. As you increase the penalty multiplier, the hope is that x star of mu, which is as a rule infeasible, starts moving towards feasibility. The barrier method also does the same thing. It starts from a constrained problem and converts into an unconstrained problem. However, it tries to always maintain feasibility. So barrier method is useful when you require feasibility. So the iterates, let's call it, are always feasible. It may not be optimum for the, of course, it goes without saying, not generally optimum. But it always remains feasible. And the idea behind the barrier method is the following. You suppose this is your feasible set. It's a convex set, let's say, and this is the feasible set of some optimization problem. What the barrier method wants to do is construct a function q of x, which is finite when x is in the feasible set. It's plus infinity if x is not in the feasible set, and it goes to infinity as x reaches the boundary of the feasible set. This is basically the idea behind, so BDRY stands for boundary of f. And then what it wants to do is it wants to take the objective function, f of x, add to it some positive multiplier times this q of x, and then minimize that over all x in Rn. And the idea here is that no matter what the value of mu is, as long as mu is positive, because q of x tends to infinity as you reach the boundary and is plus infinity outside the set, if you start from some iterate x0 which belongs to the interior of f, you will never leave it. As you start trying to minimize this function, since it goes off to plus infinity at the boundary, you're going to be pushed away from the boundary. You will never try to reach the boundary. You'll always remain on the set. So the idea now would be to start from mu equal to some mu 0, compute its optimum solution x star of mu 0, and then what would you like to do? Increase mu or decrease mu in this case? So in the penalty case, we always increase mu. We start from some mu, compute the solution, crank up the penalty multiplier, start the next solution, crank it some more, get the next solution, and so on, and start pushing it back into the feasible set. Here you're always feasible because you're not allowed to reach the boundary. It goes off to plus infinity at the boundary. This function goes off to plus infinity at the boundary. So whatever be the positive value of mu, as long as it's not 0, you're guaranteed that you would not reach the boundary. So you start from some value mu, and then do you reduce mu or do you increase mu in this case? Reduce mu. You're adding something to the objective function. You want to make this perturbation as small as possible. Unlike in the penalty case, this time you're actually changing the objective function in the feasible set. The penalty multiplier case never changed the objective function in the feasible set. It just changed it outside the feasible set. Here it's going to be changed inside the feasible set. So the next thing you do is reduce. Mu of 1 is some beta times mu of 0, where beta is less than 1. Compute the next one, x star of mu 1, and so on. Now, you don't ever want mu equal to 0, because if mu is equal to 0, you're not getting the boundary effect. You're letting the boundary go off. The boundary is forgotten if mu is equal to 0. As long as mu is positive but a small number, things would be okay. So do you expect this method to ever give you an optimum solution? If mu is not 0, no, you're always adding something. So you always get a feasible solution, but you will typically never get an optimal solution because q of x is not 0 unless you're lucky that this is that one point on which q of x is equal to 0. Generally, q of x is just finite, not 0. And so typically this method gives feasible and epsilon optimum. You give me any optimum, any epsilon you want, and this method can produce for you an epsilon optimum solution, meaning that the objective value is within epsilon to the optimum. Yes?
Can you explain the second step, how the beta fitted in?
Oh, beta is just some arbitrary thing. All I wanted to do is reduce from mu 0 to get a smaller number mu 1. And in practice, what you do is just scale it down. So the next one, mu 2, would be beta times mu 1, and so on. It's just convenient to think of coding it this way, but it's not. Okay, so what we don't want to do is create a barrier function for every possible feasible set that you come up with. So typically people construct a barrier function for just the simple case and then construct barriers using a simple barrier function. So here's what we're going to do. We're going to look at this feasible set, x greater than or equal to 0. So we're going to create a barrier for this set, x is greater than or equal to 0, and convert everything else into something that looks like that. One very easy barrier for this turns out to be q of x is equal to minus log x. So that function looks like plus infinity and then goes down this way. So notice q of x, except at this point, q of x is not equal to 0 except at x is equal to 1. And this is why you don't expect the barrier method to give you an optimum solution. It's only at one point the barrier function is 0, and therefore it perturbs the objective function inside the feasible set. Don't expect it to ever give you an optimum solution. What is this thing doing? It's going off to plus infinity. So as you start entering from this side, suppose you start from some x bar strictly positive, and you start moving here, and you're trying to minimize a function, you will never try to go to 0. You'll be barred from going to 0 because this goes off to plus infinity. Another popular function is q of x equal to 1 over x. So again, this thing looks like that. Again, as it's going to plus infinity as x goes to 0, and so on. So now let's do the same thing, the example that we did in the morning using a penalty method, and now let's do it using a barrier method. So here is the example. The constraint problem that I'm after is maximize some function f of x such that x1 squared over 25 plus x2 squared over 16 is less than or equal to 1, x1 is greater than or equal to 3.5, and x2 is greater than or equal to 2.75. And what I want to do is construct a barrier of this kind. F mu of x is equal to f of x plus or minus, I'll have to decide what I'm going to do, q, some q function, either it's the log function or it's the 1 over x function. What will sit inside here in the bracket over there? If I'm looking at the first constraint, what do I want to put into the bracket there? And there's a mu outside. So what I want to do is, as I hit x1 squared plus 25 plus x2 squared over 16 equal to 1, I want this thing to go off to plus infinity. I want it to remain finite if that constraint is satisfied. Since the barrier is for x greater than or equal to 0, you'll end up writing here 1 minus x1 squared over 25 minus x2 squared over 16. As long as this quantity is positive, you get something finite. This quantity being positive means that this constraint is satisfied. If this quantity threatens to become equal to 0, which means that you're hitting the boundary of this constraint, this q function is going to go off to plus infinity. So you will never be allowed to go to the boundary of this constraint. You'll always stay on one side of it. Now, if I'm trying to maximize this function, do I want a plus sign here or a minus sign here? So what do I want? So the way to think about it is, so here's what you want to do. We'll argue out whether it should be plus or minus. What you want to do is you want to maximize f of x, right? So that means mu should be small, but let's not worry about that. I'll take care of it by an iterative process. But what I want to do is I want to get the maximum within the set. I don't want this guy to go off to the boundaries. If I put a plus sign there, what's going to happen? As you start hitting the boundary of this, it's going to explode to plus infinity. So instead of trying to remain in the feasible set, I'm going to try to go off to the boundaries, because plus infinity for me as a maximizer is better than whatever finite number f of x takes. So I don't want it plus, because I want to stay inside the feasible set, not run off to the boundaries of the set. So you're going to take a minus sign here. And then it's just a repetition after that. Minus mu. What's the next one going to be? How would we write up the next constraint? Q of x1 minus 3.5. As long as it's positive, I'm happy. As I start hitting the boundary, I don't want to stay there. Minus mu times q of x2 minus 2.75.
So could you just explain once again why minus is so?
Okay, so what's happening here, let's just try to, I'm going to draw out a picture for one dimension that might make life a little easier to understand. What's happening here is this. Let's say I want to maximize or minimize, in this case it's a maximize. So I want to solve this problem. Maximize f of x such that x lies in the interval a, b. Here's a, there's b. So I put two barriers. So I have this barrier, log of x minus a, and minus log of x minus a, and minus log of b minus x. So those are my two penalty multipliers. Barrier functions. Those barrier functions look like this. This is the barrier for this one, log of x minus a. here is the barrier. So this function here is minus log of x minus a, and this function here is minus log of b minus x. Okay? Inside there is some function. Here's my function f of x. So I want to maximize this function in this set, so I want to reach here. That's basically the idea. So if I put a plus sign up front, then I'm adding this function, and that function. Basically, if I put up mu times and add it up, then I'll get a composite function which will look like going out to plus infinity, something like that. And if I try to maximize that function, I'm going to run off to the boundaries. It's always better for me to stay at the boundaries. And in effect, I'm losing all information about the function f of x. So if I'm trying to maximize an f of x, I want to push it into the feasible set. What do? I make the value at the boundary minus infinity. I don't like to be at the boundary, so if the values at the boundary is minus infinity, I'll go into the set. And therefore, I put a minus sign here. Minus sign would make sure that as soon as I hit the boundary of this constraint, this particular function would go off to minus infinity. So I'll run away from that boundary, I'll run away from this boundary, I'll run away from that boundary, I'll remain in the meat of the set. All right? So the trick, I mean, it's actually a pretty simple idea. All you're saying is you create somehow a barrier for x is greater than or equal to 0. All of these functions can be made to look like x is greater than or equal to 0. And the barrier method, what it says is that as long as you stay inside the set, then I can crank down my barrier multiplier mu to a point where you're pretty close to optimum, but never optimum. Because q of x is not equal to 0 inside the feasible set, and therefore you'll never get the optimum point. The penalty question.
I'm just wondering if it's better to take log of fx as well, because you have a scaling issue in terms of that mu.
Well, it depends, and that's actually a very good point. Should you take the log of fx? Well, the big problem with taking log of fx is that what if fx is negative? But what you're saying is absolutely true, and there is this thing called, the most interesting idea here is something called sequential unconstrained minimization technique. So this is sort of perhaps the best known barrier technique. And there what one does is somehow figures out a lower bound on f of x on the feasible set. Some good lower bound. And then just subtract out that constant from f of x. So as far as maximizing or minimizing a function goes, whether you're trying to minimize f of x or f of x minus the lower bound, it's the same thing. But f of x minus the lower bound is now a non-negative function. So what you do is you find out, somehow get an estimate. Doesn't matter, you don't know exactly what it's going to be, but find out some theta which is less than equal to the minimum of x in f of x. And now what you define your f mu of x to be f of x minus theta plus whatever junk. So this guy here is now greater than or equal to 0. And now this problem of f of x being negative is gone. You can take a log, make everything very balanced, and you can get an answer which looks good. There were some notes in this lecture which have currently been hidden, but in those notes there was a technique which shows exactly how to do this. From your perspective, from the perspective of simply using it, the thing to keep in mind is that often barrier techniques work very well because you don't have to worry about constraints. Okay, before we go further with this stuff, how does one deal with equalities here? So I gave you an example of inequality. What if there was an equality? What will happen then? Make two equalities. What will happen then?
We use a function
1 over, yeah, you can make it two equalities, or well, if you reflect about it for a moment, what happens is that you want, in this kind of barrier techniques, you want the set to be full dimensional in order for it to kind of work. If it's, every point is a boundary point essentially when you have an equality constraint. It's sitting on a lower dimensional space. So in order to use barrier techniques for when you have equality constraints, you really cannot use it in that higher space. You have to solve out some variables in terms of the other variables, and now you only have inequalities and you can work with it. Otherwise, you're sitting on a boundary, and no matter how you define it, it will be plus infinity at that point. And that runs into a problem. So barrier methods are not good if you have equalities. You have to somehow remove equalities from your problem. Most practical cases it's okay, because in most operational details what happens is that the equality constraints typically come from some kind of, they typically are equalities which are linear, and if they are linear equalities you can solve out and replace the other guys in terms of these linear equalities. If you have nonlinear equalities, then you're in pretty bad shape. You want to get out of that as much as possible. But if that's what you have to live with, well, can't do anything about it. Okay. Question. Yeah?
In the penalty method, how do we deal with equality?
Oh, penalty method, it's easy. Penalty method, so suppose you had a constraint of this kind, gi of x must equal bi. The penalty for that is gi of x minus bi, absolute value, or absolute value squared, whatever you want to do. Because this can now be written as gi of x is greater than or equal to bi, and gi of x is less than or equal to bi. Put a penalty for that, put a penalty for this. You can't do a barrier for both. Because if you put a barrier for this and a barrier for that, you end up getting two barriers going off to plus infinity. Doesn't help anything. This fellow is trying to push in this direction, that fellow is pushing in that direction. You sit at this plus infinity point, and it's not going to happen. Okay. The last topic about nonlinear programming is, which will lead us into integer programming, which is the next topic, is methods for separable programs. So here's the story of separable programs. So a separable program looks like this. All the constraints, so you want to maximize or minimize a function f of x which is separable, meaning you can write it as the summation of n different functions which all depend on only one variable xi, such that you have got a bunch of constraints. Let's say gi of x, let's make this j so that I can differentiate between I and j. So gi of x, which looks like a summation of j going from 1 through n of gij of xj. And let's just say that that's greater than or equal to bi. And then you've got some equality constraints. Equality constraints anyway are bad, so even in separable problems it's a bit of a problem. So what the separable problem says is the following. Effectively speaking, if you look at this entire problem, you just have nonlinear functions of one variable. So if I can somehow approximate for you a nonlinear function of one variable, I can construct an approximation for separable problems. You just use it for every variable one at a time, and you construct an approximation. So let's just think of one function g of x of one variable. Here's x, here's g of x. And let's say this function looks like that. So what the idea for solving separable problems is to construct a piecewise linear approximation. What you do is divide up this entire interval into pieces. They don't have to be all the same size. It doesn't matter. And in each of these pieces, you approximate it by a linear function. Okay? So this function can be written as, let's call it g, what notation did I say? I didn't put a notation. Let's say g hat of x can be written as some constant g hat 0 plus summation of k g hat k of x k. And what is xk? It's simply the contribution from the kth piece. So this is the first piece, the second piece, the third piece, the fourth piece, and the fifth piece. So let's say you start from this point. That's the smallest value of x you allow. And xk here is the contribution of the kth piece. So suppose you were looking at a point here. You want to find out what is the value of the function g hat of x at that point x. What you start with is this point, and that value here is g hat of 0. Let's say the total size of this interval is x bar of 1. The total size of that interval is x bar of 2, x bar of 3. That goes up till here, and then the last part here we don't know yet. Okay? So then this particular thing can be completely represented by looking at the slopes of these guys. So this will be g hat of 1, the slope here would be g hat of 2, this here would be g hat of 3, and this here would be g hat of 4. Those are the slopes. So this is the initial constant, or the what do you call that thing? The slope and intercept. This is the intercept, and these are the slopes. And if I want to write out what the function of g hat at that particular value x is going to be, it's going to be g hat of x is equal to, take the first point, which is g hat of 0, the intercept, that's this, add to it this length, which is going to be g hat 1 of x bar 1, the largest that is allowed to be in the first interval. Add to it this change, which is g hat 2 times x bar 2. Add to it the next piece, which is g hat 3 x bar 3. And finally, you just take g hat 4 and go only up to x, which is just this little interval. All right? So that's how you can represent a piecewise linear function. Now, the other thing we're going to say is that these contributions, xk, so contribution from the first piece has to be between 0 and the largest allowable, which is x bar 1. Similarly, the contribution from the second piece has to be between x bar 2, and so on. Each little xi has to be less than its upper bound x bar I. All I'm doing is cutting it into pieces, and I'm saying look at the length from each piece that you're using. Make sure that the length that you're using from each piece is non-negative, because you can only go in this direction, and the maximum that you can use from each piece is the maximum allowable length of that piece, which is x bar 1 here, x bar 2, x bar 3, and in this case it's going to be x bar 4. And what is the value of x itself? The value of x itself is just simply the contribution from each of the pieces. I going, or sum over k, x bar k, or xk, not x bar k, xk. All right? Now, what happens is that each of these approximate functions are going to be linear in the x's. So you replace these constraints by their corresponding linear approximations, and you end up getting the following thing. Notationally it's going to become tough, because you're going to, here's the algorithm that you use. Split each dimension into smaller pieces, into smaller intervals. Construct piecewise linear approximations for the functions fj of x and gij of x. For each dimension and each constraint, you construct this piecewise linear approximation. Once you do this, you just replace this separable problem by its particular approximation. So what you're doing is the objective gets replaced by max, min, sum over j going from 1 through n, and for each of these fj you have a k-wise split. So it's going to be f hat of j. It's going to be a messy thing. In here it's going to be f hat 0 of j plus summation of f hat k of j x kj. K taking values from 1 through p if there are p pieces.
So that's pj because
every one of them could have different pieces, yes. You don't have to have, yes.
Can you write it a little bit larger?
Little bit larger. Okay. So you're writing this summation, which is a summation over functions j going from 1 through n. For each j, you're going to get a set of pieces. So that's going to be f j of 0 plus pieces k going from 1 through pj, depending on number of pieces that you constructed, of f hat jk x jk. That's what you will do to the objective function. It's the same thing, that this kind of a construction, but for every fj there will be a separate construction. For the constraints you do the same thing. So here you will have, for every gi you construct a piecewise linear approximation. And next week in the homework you will actually construct it for a simple problem, and you'll see how this works out. I'll give it to you slowly and you will understand what is happening. And it's probably better for you to just do it rather than me doing it in class. But the thing that, and then what we're going to do is, first you do this approximation, second you do that approximation, and third you're going to say, put in these constraints, that for every variable xjk has to be less than the maximum allowable for that particular interval. This is basically saying that for every variable or every dimension, contribution from a piece has to be less than the maximum allowable length. That's all it's saying. Okay. Although it doesn't quite look like a linear program, it's really, after you've made this approximation, it's now a linear program. All of these functions are linear now. This was a nonlinear function, that is now a linear function. These were nonlinear constraints, this is now a linear constraint. These are some additional linear constraints that you have thrown in. So this whole structure, it may be ugly, but it looks linear. Question?
You have to separate the single one constraint into n variables. They represent separately.
I don't understand your question.
Because I thought you were going to separate every dimension.
Yes, so every dimension has been separated out. This is dimension j, kth piece.
But you still have a one large constraint, so not in every single.
These are every single, see, if this was one large constraint, I could not approximate it by piecewise linear. The reason I can do it by piecewise linear is because there is an addition here. So once this, I can approximate this function, which is just a variable, just involving one variable, and I just add them up.
So this is still not equivalent to n of the single variable optimization problem.
I never said it will be n single variable. I just said I can approximate it by looking at variable by variable. So the approximation is done by looking at variable by variable. The reason I could not do it for a general function is because if I try to find a linear approximation for a general nonlinear function, I have to find polygons in n-dimensional space. Here I just have to look at intervals. And intervals are much easier to find than polygons. And therefore, you can do it for separable, but you cannot do it for general nonlinear. Question?
Can you explain how the algorithm proceeds in the sense of what is happening at each step?
Okay. How does this algorithm proceed? For the moment, let's assume that the algorithm doesn't proceed anything except that you just dream up these intervals. And what does the dreaming up this interval involve? How accurate do you want the answer to be? You just decide on an accuracy level. You find these intervals based on that accuracy level. You construct these linear approximations, solve one big huge LP, and you're done. Okay? For now, I want to discuss one little topic, and then I'll come back to this issue of how does the algorithm proceed. So for now, yes.
Do we have to worry about the boundedness? The domain is not finite, right? Or we don't know that ahead of time?
Right. Then if you don't know whether the domain is finite, you have the issue that at this point, what do you do? Let's say afterwards, right? So that's okay. You can make one of these plus infinity. You can allow some of these to be plus infinity. Similarly, over here, you can just choose your favorite point. From there, you can have an interval going off to minus infinity. So you have to do two kinds of approximations. First, what is the domain over which you want to approximate this function? And outside of it, it just goes off as a linear approximation. But there is something more serious that's wrong here. So if I represent this function by this LP, I just want to make one little point, and then I'll go into the details of how everything else works. Is this a faithful representation modulo the approximations? Modulo the approximation that there's a linear approximation. Let's say we are willing to live with that. We are happy with the approximation that has happened. There is unboundedness issues. Let's say we are happy with that too. Given both of those, would you still be a bit nervous about using this? What will happen? What is one important thing that we have not put into this ingredient? And if we put it in, this problem becomes very hard. So we don't want to put it in. Yeah.
Negative issue as well.
Meaning?
You made an approximation that all of the lengths are going to be positive or something.
But that's okay, because all I'm saying is I'm starting from here. The left-hand endpoint is my reference point. So negative is okay. It's not that serious. But there's one little thing that when I was constructing this thing, I was assuming something in the construction. When I constructed this function value at this point x, what did I do? I started from this point, which is my last point. I said, first use up the first interval, then use up the next interval, then the next interval, and then you use up this. Okay? This is how I constructed the fact that g hat x would look like. Is that present here? Is that fact present here?
No.
So what is absent from there to here? What extra thing do I need to put in order for the construction that I made here to be exactly representable in this LP? What extra thing do I need? The order is important, but what about the order? What extra? Suppose I wanted to just represent that here. What extra constraint do I need to put?
Continuity.
What?
Continuity in the boundary.
Not quite. Much simpler than that.
The sum of the x's are.
Some of them, the sum of the x's. So basically think of this. What do I want to do? If I'm using a positive amount of x4, the fourth interval, I should have used up everything else before that. Before I start using something in the fourth interval, I should have filled up everything before. That's when this representation works. Otherwise, this representation is not correct. When you look at this LP, all I'm saying is that the contribution from each piece must be less than its upper bound. I'm not saying anything about, well, you can't. So basically what I want is something like this. xjk greater than 0 only if xjl is equal to x bar jl for all l less than equal to k minus 1. The contribution from the kth piece for the jth variable can be positive only if the contribution from the lth piece for the jth variable is equal to its upper bound for all less than equal to k minus 1. I should have filled up everything up to this point before I start using the next one. It's only in that situation is this kind of approximation exact. Otherwise, it's not exact. It's doing some bizarre thing. Without this constraint, what this is doing is it can take something from here, it can take something from there, and nothing from in the middle. Then I'm not getting an approximation for my separable function. So I have to put this extra thing. This extra thing is very annoying. If I have to put that for every piece, that's not going to give me a very good optimization problem. So there are two solutions possible. One, if I have to live with it, then I have to figure out some way of putting it in. Or let's try to look at situations where this is not necessary, that I can drop this and nothing wrong will happen. This is like saying, this is an extra constraint that I need in my problem. I'll relax it, I'll ignore it, I'll find an optimum solution, and somehow, magically, in the optimum solution, this will be true. That is, if I use a piece, everything else before it would have been used completely. So what kind of problems would that function is strictly increasing? Anything else? Anything more general than that? Somewhat?
Monotone. It should be somehow monotone.
Yeah, which is increasing or decreasing, it doesn't really make a difference. It should be monotone. Something a little bit more general than that? Our favorite functions. It should be a convex optimization problem. If each of these functions, in this particular case, since we want concavity, if each of these functions is concave, and if you are looking at minimization, then each of these functions is convex. If you're looking at maximization, then all of them is concave, then I can ignore this. I can forget about that. And the basic intuition is that in a concave function, things are increasing. Let's say in a one-dimensional case, so you'll try to fill up the bottom before you start using the top. Similarly, for convex function, things are going down, so you will try to go to the left as long before you start putting things in the bottom. So it's some kind of monotonicity, but a little bit more general than monotonicity. Monotonicity is convexity. So this transformation works if the optimization problem is a convex optimization problem. So if it's a convex separable problem, then you can do this transformation, solve this LP, and you get an approximation. Next issue now is how do you figure out where to put the breakpoints? That's a more practical issue. Start from a very coarse set, find the optimum solution, look at that interval which is currently active. So for example, if you solve this at this level and you found that this solution comes in here, then it's almost not really in your interest to refine the solution more here. You might want to concentrate only in certain region around here to refine it more, construct a new approximation that way, and keep going. When do you stop? It all depends on the problem that you're at. There are no general stopping rules for these kinds of approximations. Once you get down this road, you're almost saying that anything reasonable is okay with me. So when you look at this length being, this interval becoming small enough, you can stop. For particular problems, you can give rules. For general, you cannot. All right? This part here I'm not expecting that you would know what is happening until you do a homework problem which will ask you to construct separable approximations. The only point that I wanted to make here is that this approximation is fairly simple. I can write out an expression, but it works only if it's a convex problem. If it's a non-convex problem, then you have to worry about how do you put this constraint that this can be used only if that is full. Otherwise, it must be 0. And the way one can do that is if one switches from using continuous variables to using discrete variables. Discrete variables are one way you can have an either-or choice. Here we are making a choice. Either x4 must be 0 or x4 can be positive, but if x4 is positive, then something else should have happened. So when you're choosing between several different situations, 2, 4, 5, whatever it may be, what you need are variables that take only discrete set of values, not a continuous set of values. Here, so far, everything what we have done, linear programming, nonlinear programming, all of them use continuous variables. deciding to do one or the other using continuous variables is impossible. It continuously goes to 0. There is no way you can differentiate between 0 and something slightly away from 0. But the way to do it is to get into discrete variables, and there are many applications where you absolutely need them. So the next story that I want to talk about, and by the way, this is where I end nonlinear programming. You will do a bunch of it in the homework this week, and another bunch of it in the homework next week, which will probably gel things a little bit more. From the point of view of what do I expect you to know well for the exam is quadratic programming. Everything else is, it's sort of things that you should be aware of, and I'll give you problems to look at, but it's nothing very deep will be asked out of those issues. Okay? It's sort of at the level of what the homework is going to be, nothing more than that. Okay, so now let's open the story of integer programming and see that for a little bit, and then we'll quit. Okay, so what we're going to do is just look at examples and try to get an idea of why are integer variables interesting. So here's the simplest example, and that we're going to be talking about. So we're looking at an investment problem which has the following structure. I just want to invest in 3 mutual funds, M1, M2, and M3. These mutual funds have a minimum investment requirement which says the following. Either you invest L1 amount of money in the mutual fund M1 or don't invest at all. If you decide to invest in this mutual fund, you must invest a minimum of L1. And then it has a fixed cost, a front-end load. You pay a fixed cost to getting into this mutual fund, and then there is a proportional cost. For the modeling purposes, let's just assume the proportional cost doesn't exist. Proportional cost is something that I can do using continuous variables. So that's not something new that will show up here. And then the return vector of these 3 mutual funds is R, boldface R, the covariance matrix is V. I have to allocate a total wealth W to ensure a return of R with the least risk. These 2 lines here basically should signal to you Markowitz. You are given the mean vector, you've been given the covariance matrix, you've been told find a minimum return with least risk, just tells you Markowitz. Except that in mutual funds you can't short it, so you have trading restrictions that you can only put non-negative amounts in there. From the point of view, if this wasn't there, if these 2 statements weren't there, if there was no minimum investment requirement and there was no front-end load in terms of a fixed cost, then this problem could have been solved during solving a QP. QP with side constraints saying that the amount that I invest in M1, M2, and M3 must be non-negative. Now, when I look at those 2 situations, minimum investment and the fixed cost, I have a problem where I have to introduce variables which take values only 0 or 1. Because I have to differentiate between 2 situations. Do I invest in the mutual fund or do I not? If I do invest in the mutual fund, then the amount that I must invest must be at least Li, where Li is the wealth corresponding to that mutual fund. If I decide not to invest in the mutual fund, then that could be 0. So I have to differentiate between these 2 cases, and that's why I need discrete variables. So before we go into discrete variables, let's try to convince ourselves that we cannot do it using continuous variables. Let's try to see if we wanted to do this using continuous variable, whether it'll be possible. Let's try it. That's why I'm saying let's try it before we convince ourselves that we need 0, 1 variables. Let's try to do it using continuous variables. So you're suggesting there is a method. Let's try it.
I suggest that we add a shift because the minimum we have to invest is.
Sure. Let's give me the decision variables that you want to use, and we'll use it that way.
We just use some L cap.
Yeah?
This L hat that has to be.
No. Give me particulars. So so let's define xi to be the investment in mutual fund I. Okay? Those are my decision variables, let's say. So what are my conditions, my xi?
Greater than M1.
Oh, m's are just the placeholder.
L1.
So xi must be greater than equal to li. Does everybody agree that that is the only constraint on xi?
It can be 0,
It could be 0. So either xi is greater than equal to li or xi is equal to 0. That is the constraint on xi. Right? If I do invest, then it must satisfy, let's put some numbers, make things easier. Let's say L1 is equal to 5,000, L2 is equal to 2,500, and L3 is equal to 3,000, and W is equal to 15,000. Just to make everything. So what this is saying that either x1 must be greater than equal to 5 or x1 must be equal to 0. Okay? Now let's see how we can put that into an optimization problem. Of course you can solve 2 to the 3 optimization problems in this case and get the answer, but I want one optimization problem that will do it. Can we do it using continuous variables? Anytime you have an or, anytime some or shows up in an optimization problem, it should signal to you that you have 2 different cases to consider. The moment you have cases to consider, and if you want to write it as a single optimization problem, you need to have variables that take only 2 possible values. So in a way you can think of x, but you can think of a continuous variable as different possible situations the investments could be in. Here we are saying that either x must be greater than or equal to 5, which is fine. It could take 5 and whatever continuous set of values. Or there is a gap in between, it can be 0. So you have to somehow differentiate between whether you're in the 0 state or you're on this other state where you're allowed to have non-negative investment. So differentiate between these 2 conditions, you need a variable. And let's call that variable y1. y1 in this case would be 1 if positive investment in mutual fund 1 and 0 otherwise. So this variable is simply deciding between which of these 2 cases have I landed myself in. Have I invested? If I've invested, then I have to make sure, oh, that's yi, so let's make this I. So far I've just thought up this variable, that this variable would somehow help me. It will differentiate between this, whether I'm in this case or in that case. But in order for me to use this variable in an optimization problem, I have to connect this variable to that somehow. I have to be able to say, I have to add conditions so that yi equal to 0 implies that xi is equal to 0 and yi equal to 1 implies that xi must be greater than equal to li.
You could do a product, but that would be nonlinear, right?
Yeah, you can do a product, but that would become a nonlinear. So I don't want nonlinearity right now. I want to use linear constraints still. So how would one impose this connection between the yi variables and the xi variables? So this part here is kind of easy, right? You can write this, you can start off with this kind of relationship. Xi is greater than or equal to Li times yi. It sort of makes sense. If yi is equal to 1, at least I've ensured that xi is greater than or equal to Li. But when yi is equal to 0, then that constraint simply says that xi is greater than or equal to 0. What I want is a stronger condition. I want a condition which says that if yi is equal to 0, then xi is equal to 0. It's not allowed to move. So what does one do to impose that? So what one wants is an upper bound. The lower bound took care of this. So you want to be able to put something up top here such that when yi is equal to 0, so what we want is something like this. We want to be able to say li is less, li yi is less than equal to xi, which is less than equal to some upper bound times yi. Right? Some m is some big upper bound. If I'm able to say that, then if yi is equal to 1, then I know that li is less than equal to xi, which is less than equal to m. And if yi is equal to 0, then both of this become 0 and xi is equal to 0.
Even the wealth upper bound.
So total wealth is an upper bound in this case. But suppose I could hold short positions. Then you can't do it.
You cannot.
Well, okay, this wasn't mutual funds. Let's say there's some other situation. So in this mutual fund case, indeed, I can replace the M by a W, the total wealth. Because I'm only allowed to hold long positions, which means that the total investment on any given mutual fund is going to be at most the wealth W. And so I end up getting this constraint. Okay.
Can you explain how you got this?
How do I get that? Much of it in integer programming, unfortunately, is guesswork. But I can give you some idea of how I got it. So let me just reiterate the steps that we wanted. So the thing that we started off with was this, that xi is the investment in mutual fund I, and these are the two situations that I want. Either xi must be greater than or equal to li, or xi must be 0. In order to differentiate with that between those two, I introduce a new variable yi, which takes value 1 if invest, and 0 otherwise. So it's important to remember that so far when I create this variable yi, I'm just dreaming up this variable. It is not at all connected to xi. I'm just saying that this is what I want yi to be. Whenever I'm thinking about investing, I want yi to be 1, which means in this case this should happen, that xi must be greater than or equal to li. If yi equal to 0, which means I'm not investing, and in this case that must happen. So I have to somehow connect the xi variables with the yi variables. This part here is relatively easy. All you're saying is you start off with some constraints like this. Xi is greater than or equal to li times yi. Then I ensure that this will happen. If yi is equal to 1, then that will happen. Now what I want to do is, so the first part is like saying that if yi becomes high, I want to push my xi to be large. So that will give you this. The next thing I want to do is if yi is small, meaning yi is 0, then I want to push the xi down. So I need an upper bound on xi. So let's just pretend that there is some big upper bound, m. And if I multiply that by yi and put this constraint, push xi down when yi is small, then I have made sure that if yi is equal to 0, then this is equal to 0. yi is equal to 0, you get a 0 from here, you get a 0 from there. But then I've caused myself this other problem as to what is this m. So if yi is equal to 1, then I get this constraint. xi must be greater than or equal to li, which is fine. This is what my problem said. But now I get an upper bound saying m. This must be less than or equal to m. That wasn't there in the problem. Not there explicitly anyway. So what I want to make sure is that I choose an upper bound m such that by putting that upper bound, I'm not restricting my choices for xi in any way possible. So in this particular example, it turns out that this is mutual fund. You can only invest long positions, which means that in any given mutual fund, you cannot invest more than W, more than the wealth that you start off with. There. And so I can use W as my upper bound. Okay? All right. So if you do all of that, then once you have created these yi variables and you have connected the yi's to the xi's, then you have this interesting thing that you can now start using yi to represent the fixed cost. You pay a fixed cost only if you invest. You don't pay the fixed cost if you don't invest. But since yi takes a value 1 only if you invest, this product here represents the situation of paying a fixed cost only if you invest. The rest of the junk here is basically proportional transaction cost, which is something that we have done even before. So putting all of that together, you end up getting this optimization problem. This is just the budget constraint, which says the fixed cost plus the proportional cost plus the investment has to be less than or equal to W. This one here says that the expected return must be greater than or equal to R times W. And here you're just saying that YI's take values 0 or 1. Okay? Question?
The second constraint, the Y is less than or equal to W.
Budget constraint. Total budgets. So the total budget is XI's is what you invested into the mutual fund. For that you paid a proportional cost of alpha I XI and you paid a fixed cost of CI YI. Added all of them together, that must be less than the total wealth that you began with. Okay? What? Oh, that's the return that that was demanded of you. Right here. It was asked that you get a return of capital R. Okay. All right. The thing to sort of this example, the only thing it's saying is that this integer variables or variables which take value 0 or 1 become important when you're trying to choose between 2 or 3 different cases. Let me see what example I have next that will make my life. Okay. So here's another example of the same story, and this one actually connects up back to the story of the separable problems. So the situation here is the following. You're going to buy parts. So let's say X is the number of parts ordered. And let's say that particular f of x gives you the cost of ordering x units of parts. And let's say you have a constraint of this kind. F of x is less than or equal to b. And b is a constant. Right? You have a big optimization problem, all the various kinds of things, and somewhere lurking in that big optimization problem is this constraint. That the total cost of ordering these parts has to be less than or equal to some constant b. And the function f of x looks like this. You've got a fixed ordering cost of 10, no matter how much, even if you order 1 unit. The first 10 go up with a slope of 5. These are first 10 parts. And then you start getting a discount. So the next 25 cost $4 each. So this is 35. And the slope here is 4. And anything beyond that costs $3 each. So let's say this is 3. And for some operational reasons, you know that you're never going to order more than 200 parts. So somewhere here is 200. Okay, so this here is x, and there is f of x. For the moment, let's make an approximation that x actually takes continuous values. I'm not going to worry about x being an integer, right? Then this particular constraint is a bad constraint because it's not a convex constraint. This function is concave. A concave function less than or equal to b is not a convex constraint. And so this will give me a non-convex optimization problem. So what I want to do is convert this non-convex optimization problem into a linear looking problem with integer variables. Why? Because I look at these piecewise linear pieces and I say to myself, look, these are linear. There's a very nice structure here, and I want to leverage that structure to somehow get us easier optimization problem. So my goal now is to construct, I want to represent f of x as a linear function. So f of x must start looking like a linear function, and I cannot expect that it will look like a linear function in x only plus some integer variables. It's clearly not linear in x only, so there is no hope there. But if I throw in some integer variables, perhaps I might be able to represent it as a linear looking function, meaning that it looks like just a constant times the variable. So what I'm doing is I'm just trying to build up towards there. And in order to build up towards there, what I'm going to do is for each of those pieces, I'm going to represent it by a linear function. So I'm going to call this linear function, just extend it, and call this as k1 plus 5x. Right, that's the cost of ordering stuff from the first piece. We're just going to say the following. We're going to say, pretend as if there were three different suppliers. One supplier was giving me this, k1 plus fx. That's the cost that that supplier is giving. The second supplier is giving me this, the second function over here. And that function would look like, what's k2? Did I compute it somewhere? Yeah, it's going to look like 20 plus 4x. So this one here is 10 plus 5x. And then there is a third supplier, which is, what happened? And the third supplier here is giving me at 55 plus 3x. So three different suppliers, they're giving me three different costs. All three of them are linear. Okay? But the problem is that since I'm trying to minimize my cost, I'm going to switch between these three suppliers. If the amount of order that I get is less than or equal to 10, then I'll order the first 10 units from this guy. The next, say I have to order 15 units. So the first 10 units will be from supplier 1, and 5 units will be from supplier 2. And I will not order anything from supplier 3 until I have gone up to 35, and then I'll switch to supplier 3. Okay? So if you want to represent this idea that up to a certain point I'll go to supplier 1, then supplier 2, then supplier 3, how do I capture that using integer variables? It's sort of very similar. If you think about it for a moment, this can be thought of as if this was three different, just very similar to the mutual fund example, three different situations. I can either order from that supplier or not. And if I do order from a particular supplier, if I order from supplier 1, then the maximum I'm allowed to order is 10 units, because after that I know it's cheaper to go to supplier 2. From supplier 2, I'll go up to 25 units, because after that I know it's cheaper to order from supplier 3, and so on. So let's try this variable. So let's say xi is the number of units. Depends on how I write this.
Isn't this similar to the last problem on the...
Good question. Okay, let's answer that question before going further. I don't think I have time to finish it anyway, so I'll start this on Tuesday. But so the comment here was, isn't this similar to the last problem on the midterm? What is the difference between this particular problem and the last problem on the midterm? So in the midterm problem, what were you have? You were given a concave function. It had two pieces, right? That's actually a good distinction. So you were given this piece and that piece. And this was x, this is r of x. That was a concave function, this is a concave function. This just has more pieces than that one. Right? That one has just two pieces, this has three pieces. And in the midterm, you were told that that can be done by linear programming. This cannot be done by linear programming alone. I have to use integer variables. So what's the distinction between that and this? Why could you do that using integer programming, whereas not this one? Or, sorry, the other way around.
Because in that case we have dichotomy of whether it's in one set is happening and we use one set of problems, and in this problem we don't have a dichotomy. So.
Could you be a little louder?
Dichotomy.
But here there is a trichotomy, really. So for example, let's take, so in this case you were trying to maximize the return. Here you're trying to minimize the cost. The constraint here would look like r of x has to be greater than equal to some lower bound r. This is a piecewise linear concave function. That is a convex constraint. For a concave function, being greater than equal to lower bound r is a convex constraint, and you have a piecewise linear function leading to a convex constraint. I can do it by linear programming. Here I've got a piecewise linear concave function, but that's a cost, and I'm trying to minimize that cost. Can't do it. On the other hand, if this was a convex function, if the cost was increasing, then it's fine. Then I can do it. But typically costs, there is some reduction on scale. If you buy more, your cost comes down than the linear, so convex costs are typically not there. The only places where convex cost shows up is in execution. When the more you try to sell, the more is the cost, because somebody already knows that you're trying to sell something and they want to push you to a higher and higher prices. So I've got 4 minutes left. So might as well give you the weekend 4 minutes early. We'll start again on Tuesday.